In this portion of the text, I describe the results in a chart form with respect to the repeated sampling standard error, the mean estimation approach. And you can see that for the sample size of 5, the 10 sample means are displayed in this histogram. And we can see that there were 2 means associated with a value of approximately 6.5, 6.6, 6.7, something like that. And only 1 sample mean was as large as approximately 8. We can see there's a lot of variability centering around a mean of approximately 7.31, which is the population mean. Now, as soon as we move up to a sample size of 10, we can see that there's a narrowing in the amount of variability in the sample means, which continues on to its sample sizes of 50. There's a really big jump here. From a sample size of 10 to 50, we're really narrowing down our estimate of the population mean. And that's why the standard error of the mean for sample size of 50 was estimated at 0.16 with the resampling strategy, but it was actually as high as 0.51 associated with the sample size of 5. So the standard deviation associated with these sample means is much larger than the variability here. Now, as we keep moving on to a sample size of 100, where the standard deviation in the sample means, or the standard error of the mean, was estimated at 0.13 with the resampling strategy, we're progressively getting narrower, and then 1000, it's getting to be an extremely narrow histogram, and then moving up all the way to 5000, it's becoming needle-like. That is how precisely the population mean of 7.31 is being estimated with these random samples of 5,000 cases. So it's not only that they're estimating the population mean more accurately, they're doing so consistently. And this again underscores the benefit of a very large sample size of 5,000, but it's not really a huge difference between 1,000 and 5,000 in terms of reduction in standard error. You get the biggest bang for your buck going from 5 to probably 50. That's a huge change there. And then 50 to 100, there is a change. And of course, from 100 to 1,000, there's also a change, but just not nearly the magnitude given the extra cases that you've got to sample from the population. And so this is a visual depiction of the power of sample size in the context of standard error of the mean. And I just point out that one way to think about this is that the population mean itself is a magnet, and samples are also magnets, but the size of the sample represents the size of the magnet, and it's just not strong enough, a sample size of 5, to really keep everything really close to the powerful magnet that the population mean is. But when you get to a sample size of 5,000, a sample size of 5,000 represented by a magnet is just so strong. It has a very good attraction to the population mean of 7.31 in this case, and that will be true for every population that is estimated with sample sizes as large as 5,000.